Okay. So I like to talk about change equations, linear and exponential change on the SAT. I mean, I wish that I could change basically everything about who I am and what my life is. I wish there were an exponential change equation I could just plug myself into. But there's not. So the next best thing is I can talk to you about how linear and exponential change equations are built, about what the different components of them mean. And I think I'll start actually by talking about the different ways tests like the SAT have of signaling to you that they're talking about linear or exponential change without flat out saying it, because a lot of the kinds of questions that I want to prepare you for today are, well, are questions where they'll describe for you a situation and they'll ask you what kind of change this is, linear or exponential. Or they might ask you which equation represents the situation they describe. And maybe some of the equations and the answers will be linear, some will be exponential. And so a part of the question is you being able to tell the difference between those equations, as well as understand how the different components of each equation work. So let's start with the linear stuff. So linear change, that means like the same amount is being added or subtracted each time. So I got some sample numbers here, right? 2, 4, 6, 8, 10. I'm adding 2 each time. It's happening at a constant rate. And in fact, that's one of the ways they will whisper to you that it's a question about linear change. They'll say, oh, blah, blah, blah is happening at a constant rate. I once saw this SAT problem that was about like a copy machine, and the number of pages it spit out each minute was happening at a constant rate. Or if you are in your first 6 months of lifting and you're able to add 5 pounds to the bar each week and experience those great newbie gains, that's linear growth. And by the way, that doesn't last forever, so enjoy it. Or they might give you a graph and they'll say, oh, they'll describe some situation and just tell you, and it can be modeled by this graph, and they'll show you a line. That's, of course, another way to know that we're talking about linear growth. Or they might just give you the equation of a line, a classic y equals mx plus b equation. But of course, in classic SAT fashion, they do some superficial cosmetic changes to the highly recognizable y equals mx plus b equation so that you are less likely to recognize it, to disorient you, to destabilize you. But the way they have of doing this is pretty basic stuff that's, in my opinion, pretty easy to see through. So here I've done one here. Instead of y equals mx plus b, I've got a of t equals 19 minus 3t. So I did a couple things here. One, I am not using y or x, right? So I changed the letters. And also I've swapped the order of the mx term and the b term. So we're used to mx plus b. Well, this is b plus mx. Oh no. So you see, they do these super simple things to just make it look a little different. But it's just a y equals mx plus b equation. If it helps, just rewrite the equation in the right order, in the order you're used to. Basically, whenever they give you an equation and there's no exponents on the variables, there's no exponents on the line, on the letters, I mean, well, that's a y equals mx plus b equation, okay? So it's fine. What do the different components here mean? Well, the number without the variable, that's of course the y-intercept. So in this question here, the 19, that's our y-intercept. Y-intercept represents the starting value, the initial value, as they like to say on this test, or the value of whatever is going on when x equals 0. And it's pretty easy to see why, right? You plug in t. You plug in t equals 0, it's going to make this term disappear, And all we'll be left with is the number that's not touching a letter. The number by itself. A constant. It's another word you'll see on this test. So that's what's going on there. And the other number, the m in mx plus b, that's our slope. That gives you some kind of change that's going on, some kind of rate of change. One way to interpret slope, or one way to phrase it, is this number, in this case, -3, it tells you how the y value changes each time the x value increases by 1. So, for every increase of x by 1, y decreases by 3. That's one way to interpret slope. I've got a couple other slope videos and shorts that I'll probably link to in the comments, because the SAT loves slope, and I want to make sure you're super prepared for any slope kind of questions, because once you have that down, they become real easy questions. Speaking of comments, feel free to leave a comment if you have a request for another math concept, SAT prep concept, ACT prep, whatever you need. I got you. Just leave a comment requesting it, and I'll just get right on it. Also, if you want to email me, CoachDaltonFoster@gmail.com, you can apply to work with me. Check out my Mathochist subreddit. Please like and subscribe this channel, this video, all this stuff. If you're getting anything out of this, jeez. I want to talk about exponential stuff next. So when there's exponential growth occurring, basically what that means is the amount that's increasing is also increasing. So contrast that with what a constant rate of change means, where the amount that's increasing is always the same, constant, add 2, add 2, add 2. With exponential growth, the amount that's increasing is also increasing. So look at this. Got some sample numbers here: 2, 4, 8, 16, 32. So as you can see, we go first 2 to 4, that's up by 2. Then we increase by 4. Then we increase by 8, and so on. So the amount that we're increasing by is also increasing. That's one way to look at it. Another way to look at it is to see that we're doubling each time, aren't we? 2, 4, 8, 16, 32. Each time we're getting doubled. So there is a consistent relationship. It's just that with linear, the consistent relationship is that we're always adding the same number each time or subtracting. With exponential, it's that we're always multiplying or dividing by the same number each time. So that's the little difference there. Exponential growth often looks something like this. So as opposed to a line, which always has the same steepness, that's why slope is a thing, because you can measure how steep the line is. With exponential growth, it's getting increasingly steeper as you go on. So maybe they'll give you some sample numbers. Maybe like in a little table of values they like to do, so you can observe that the numbers are increasing at an increasing rate. Maybe they'll say that some situation, like they'll describe some kind of situation where there's out of control growth, like maybe they like bacteria kind of examples, right? So maybe they'll describe some laboratory experiment where the amount of bacteria in a petri dish is tripling every 10 minutes or something like that. Or maybe it's about the amount of microplastics that are in the ocean, or it's about the amount of Marvel movies they made every year from 2010 to 2020. Just something that's a huge problem that's metastasized and is just way out of control. Something like that. They might say, oh, it can be represented by a graph that looks like this, and you'll recognize that it's an exponential graph. Or they'll give you a table of values, and you'll be able to observe that it's exponential growth. Or they'll drop some exponential equations in the answer choices. And that's probably actually the most common thing that'll happen in a word problem about exponential change, is they'll describe a situation for you, and they'll ask you which equation represents this situation. And exponential equations look like this. You got a number before parentheses, you got parentheses with a number inside, and you got some kind of exponent, and that's where the variable is, like the x, the t, whatever. Exponential. That's why it's exponential change, exponential equation, because it's got an exponent. That's where the variable is. So the number before the parentheses, that tells you the starting value. That's just like the constant over here in linear change, the y-intercept. And again, we can see why. When you put 0 in for x, it's going to make the exponent 0. And when you put anything to the power of 0, what does that become? Yeah, it's 1. So this whole thing becomes 1, and it's 1 times that number, so all we're left with is that number before the parentheses. Look, we don't need to, harp on all the reasoning behind everything. You can just memorize the number before the parentheses is the starting value. Boom, good. The number inside the parentheses, well, that tells you what kind of a change is occurring. Now, usually in this kind of question, it's some kind of percent change. So in this case, I got 1.2, which, by the way, I hope your brain is wired so that when you see 1.2 in parentheses, you're immediately thinking 20% increase. Are you? If not, you better get to wiring the brain to think in those terms. I've got a percent change short that I should also link to in the comments. That's about that. So yeah, 20% increase. And the exponent, well, that tells you how often the change occurs. So with this first equation here, we're starting with 100 of something, and we do a 20% increase every year. If the exponent is just x like that, well, and let's say x represents years, that just means it's happening each year. Nice and simple. Now, inside the parentheses, it isn't always percent change. You might just see some straight up number in there. Like here, I got a 3. That means we're multiplying by 3. In other words, it's getting tripled, right? Which, by the way, tripling something, that's the same thing as taking 300% of it. But in percent change terms, it's increasing by 200%. Are you on board with that? Multiplying by something by 3, you're increasing by 200%. Just like how when you double something, you're increasing by 100%. You're taking 200%, but you're increasing by 100%. Is that okay? Do I have to make a whole other percent change video explaining that part? Or we're back to percent change over here, 0.85. Again, you should just automatically see 0.85 in parentheses and just think immediately 15% decrease. Boom. Now let's talk a little bit more about how these exponents work. Like we said, just the x by itself means it's happening each year, assuming x represents years. If you see something like 10x, well, what that means is it's happening 10 times a year. And that should be pretty easy to remember because it's 10x means 10 times x. If x is years, it's literally just saying 10 times year, 10 times a year, right? And if it's x over 10, and by the way, this is the kind of exponent I've noticed is in correct answers more often on the SAT. I don't know why that is. I think it's because they assume that looks a little weirder, so they figure that maybe people are going to be less likely to guess that one if they have no idea. But what x over 10 means is that the change is happening once every 10 years. So just to recap these equations over here, we're starting with 100 of something, and it's increasing by 20% each year. The next one, we start with 80 of something, and it's getting multiplied by 3 10 times a year. And finally, we start with 70 of something, we're decreasing by 15% once every 10 years. So that's about what I got for that for now.